It's a different Greek name, I know. So, compression and now tension. Unfortunately, people working with very brittle materials have to solve a problem that is already solved for people working with ductile ones. So, Nikos or the lady before mentioned 3-point bending tests or other kinds of tests in order to obtain something like a substitute tensile strength. Why? Because it works automatically. We cannot perform a direct tension test in a specimen made of concrete or of rock. It is familiar to all of us that the formula for the tensile test is difficult to be applied in a specimen made of rock, of mud. So many decades ago, Carneiro and Nakazava proposed the familiar Brazilian disc test, which is supposed to use a cylinder compressed, and theoretically speaking, at the center of the disc we have a tensile component. Unfortunately, we have also a compressive one, and sometimes fail is due to the compression component and not due to tension. The test was standardized both by ASTM and ISRM many years ago, and it is used worldwide. There is not an alternative that provides us the tensile strength of such materials. However, it is known to all of us that immediately after it was introduced, the test was very seriously criticized by many researchers. I mention here the milestone paper of Fairhurst in the first volume of the renowned journal, International Journal on Rock Mechanics and Mining Sciences. The main problems are two: the triaxiality of the stress field at the center of the disc, and also the severe stress field developed at the contact points. So there are too many papers criticizing the test, which however is used because it seems that we have no alternative. Of course, a few years after Carneiro and Nakazava, Ripperger proposed the ring test, which solves one of the two problems because at point here we have only a tensile stress component. However, the problem of severe stress concentration on the contact point still exists. That is why during the last years we have a variety of alternatives proposed to solve this problem. This is one produced by our team, but what is the problem? Trying to solve the problem, we make the geometry more complicated, and it is difficult to prepare specimens for mud or from concrete with complicated geometry. So we need something that it is also simple to be prepared for laboratory use. All these attempts unfortunately cannot solve the problem related to stress concentration, especially at the end of the contact arc developed between the loading platters of any shape and the specimen itself. So our purpose is to discuss a new geometry which we will prove that solves theoretically always, this is the theoretical solution of the problem, both issues, the stress concentration and the triaxiality of the stress of the stress field at the center of the disc. So if we have a truncated disc and the radius of the R1, the value R1 is close to R2, the value to the intenter, we have from the very beginning a very long contact arc, which means that the stresses developed at the contact area are in fact much smaller. We make some comparisons later. Also, since the curvature is inverse, we have not restrictions to the trend of the material to move apart, so we do not restrict the tensile components. And finally, what is more important, the results that are obtained from this configuration are material independent. Perhaps it sounds strange. We all know that stresses do not depend on the material, or this is what we think. But since both the platens and the material are of specific stiffness, the contact arc developed during the execution of the Brazilian disc test increases gradually, which means that the results obtained finally depend on the relative stiffness of the material. And this is of huge importance. It is not a 2 or 3 or 5%. It may obtain values up to 30% different. So, okay, we have an idea. But the main difficulty is to solve the problem. As Kourkoulis made with the traditional circular disc, we have to find the solution of the distribution of stresses within this somehow more complicated disc. And in fact, we have to solve two problems. First, we have to determine the stress field developed at the contact area. And then, knowing this field, we have to determine the stress at any point of the disc, and especially at the center of the disc, where we suppose that we will obtain the tensile strength. We suppose. So the first problem is solved a few months ago, and what we found is that the distribution of stresses, assuming R1 and R2 values relatively close, we found that the distribution of strains is somehow parabolic. In fact, it's not parabolic, it is circular. However, circular distributions cannot be solved by the complex potentials techniques, so we have to adopt a simpler one, which is the parabolic distribution. The difference is not very big, it's about 4 to 5%. So having solved the contact problem, we proceed now, this is the first attempt, and we think successful, using Markides' complex potential to apply on the disc the distribution of stresses we determined in the previous step, and try to determine the stress field all over the disc. So we substituted the distribution of stresses, the continuous distribution of stresses, with point forces, and as the number of point forces increasing, we tend to remove the importance of the shadowed part of the disc, and so to obtain the geometry of the truncated one. So, the first step when you solve a problem with complex potential technique is to determine the complex potentials. It was not an easy procedure. It took us many months to find the two complex potentials, phi and psi. And then you have to inverse the transformation from the imaginary plane to the real one. People working with complex potential understand that such complex potentials are very difficult to be inversed. So, it was done, and taking advantage of the famous equations by Markides, phi over bar denotes the complex conjugate and the prime denotes the derivative, we have obtained the stress distribution along some strategic loci. Along the load, you see that the stress concentration at the contact point is only 6 times higher than that at the center of the disc, sigma x over sigma psi, which means that we have resolved one of the two problems. Along the psi axis, which is the most important, because sigma x is supposed to be the tensile strength, we have exactly the distribution proposed by Kourkoulis, which is natural because the role of the boundaries tend to be eliminated at the center of the disc. And of course, if we study an arbitrary locus, like this one ending at the end point of the contact arc, we have in addition some shear stresses, which is very natural, but also it is very important to note that the field is bounded. We have no infinite stresses. If one has determined the complex potentials, everything is simple. Then you can also determine the displacement field. We have plotted here indicatively the deformed shape for some parameters, assuming that the lowest point is fixed, because this is the standard experimental procedure. And I would like to insist in this slide, we compare the ASTM proposal to the ISRM standardization, the standardization proposed by Wang called flattened Brazilian disc, and this approach. You can see that the stress, which is supposed to be the tensile strength at the center of the disc, is almost similar to the approach of ASTM, to our approach, and to the approach of ISRM. The one proposed by Wang somehow diverges. But what is most important is to see the maximum values developed. We have here some 750, 450, and 122 stress components at the contact area, which means that a larger variety of materials could be tested with this technique, avoiding premature fracture due to localized cracks at the disc loaded flattened contact area. Okay, you can see the role of the material here. As I mentioned, using this technique, the material does not play any significant role. And the values obtained for the tensile stress, I do not mention strength, because we are not sure that this parameter is the tensile strength, is very close to that proposed by Kourkoulis, if this is the tensile strength of the material. Who knows? Moreover, we have tried to determine some optimum geometrical parameters, because we would like to propose this as a standard, concerning the radius of the hole, the radius of the indenter, the distance of the indenter. You can see that in fact there are some combinations for which the results are very close to the results proposed by Carneiro, Akazava, and Kourkoulis, very close to this 9.5 megapascals. So, coming to an end, we believe that this geometry, which is relatively simple, not as simple as the one introduced by Carneiro, because we should groove somehow the specimen. However, it seems that it cures the main drawbacks of the previous proposal. What are the drawbacks? Severe stress concentration and the role of the material. The theory is now available. The next step is to execute some experiments to see how close is the theory, and more important, to execute direct tension tests. Because in order to compare our results with Stavros means that we accept that the Brazilian disc provides the tensile strength. I'm not sure about this. The only actual value of the tensile strength is the direct tension. Everything else is a substitute. Whether this is a property of the material or not, it's not sure. So, the next step is to find the material very brittle, marble, concrete, prepare, it's very difficult, direct tension tests, and then test our results and that of Stavros to see whether we can provide with this, let us say, parallel way, the actual tensile strength. Thank you.
Thank you. I think it's not a problem of geometry, because you can realize formwork to have this geometry. So
no, it is not only concrete. For example, we test many times marble for the restoration of Parthenon.
Yeah.
It is very difficult. For example, we have some geometries with double shoulders, but the success is 1 over 20 specimens, because even the slightest misalignment creates shear stresses in marble and rocks cannot sustain. So it is not very easy, but we have to do it. We have to do it. For concrete, it is easier.
Not a problem. Any question from the floor?
Nikos?
Okay.
It was clear enough. Thank you.
Thanks.